Going to get started. Couple things. So first off, your homework 7 is due now. So if you haven't already done so, you need to put your MATLAB scripts in the network drive. If you recall with the last homework, there was a few of you that for that second problem you had put just a screen clipping of the MATLAB script, and then we extended the deadline so everybody could put the actual program in. There were still a couple folks that put the screen clipping and didn't actually put the script into the network drive. We need the actual script, so for grading purposes. So just make sure you've got your script for homework 7, everything in the drive. I'm going to go through the homework 6 solution really quick here in a second. But a couple other things. So homework number 8, what I'm going to do is I'm going to assign that homework Tuesday, and it's going to be due the last lecture, that last Thursday. So homework number 8, that's our last homework. Okay. So today we're going to sort of cover, I don't know if filler material is the right word, but just some stuff that we need to have just some requisite skills we need to have before we start doing some real final stuff with MATLAB, particularly with saving and loading data and doing for loops and things like that. All right, so everybody good with that? All right, so let me real briefly go through the homework 6 solution. What I did for the solution, if you all go to Blackboard, you'll see there are 2 PDFs posted. The first PDF is literally just from the command window. You know, you can see, for instance, each of those commands being put in and the answer following that, so you all can sort of follow along and see where I guess you went right or where I guess you went wrong. I think that was a pretty straightforward problem. As for problem 2, what I did is I just PDF'd the code. So here's your code. Now, I mean, you didn't have to verbatim, enter foundation width and feet. If you just put enter foundation width, that really wasn't a big deal. But this will just give you an idea of making sure that your syntax is correct, that you're using semicolons where you need to use them, that your if statement makes sense, and so on and so forth. So, so there is that. Anybody have any questions about this homework assignment? I think this was pretty straightforward. Hopefully it was. Hopefully this was pretty simple. All right, sound good? Okay. All right, so let me get the sign-in sheet started. So today what we're going to talk about is we're going to talk about 2D matrices and what all we can do with them. And I think you'll find that if you understand everything that we did with 1D matrices with vectors, like if you wanted to create a vector from 1 to 10 and you wanted the values spaced out with an increment of 0.25, you could create that quite easily. If you understand all of that notation and all of that syntax, then I think what we do today is not going to be too bad. It's just a little more, I guess I would say. A 1D matrix, or a vector, as I was calling it quite a bit throughout the last couple of lectures, is essentially just a row of numbers, or in some cases a column of numbers. Well, a 2D matrix is just a big table of numbers. And if you can, like I said, if you can deal with vectors, you can deal with matrices. They're pretty straightforward. There's a few notational quirks, I guess, that we ought to make sure that we're all clear on. But all in all, I think you'll find this is pretty straightforward. So first off, if you haven't opened MATLAB yet, you're going to want to do so. So go ahead and open MATLAB. Now we're going to create a simple 2D array. Where, like I said, you probably won't hear me use the word 2D array. You'll probably just hear me call it a matrix. So we're going to create a matrix, and we're going to manipulate it quite a bit. Now, here I've got a matrix. Now, just so everybody's aware in terms of terminology and how we refer to matrices, this matrix has 3 rows, 1 row, 2 row, 3 rows, and it has 4 columns, 1, 2, 3, 4. So we would say that this matrix is a 3x4 matrix, 3 rows and 4 columns. Okay. Now, we know how to create one-dimensional matrices or vectors. We use square brackets and we use commas to separate all the values, right? Well, we basically do the same thing for matrices, but if you've noticed, we've got multiple rows. So the way this works is you go in and you define each of these terms, and you can separate them with a comma. And then once you get to the point where you need to create a new row, you insert a semicolon. So here's how this matrix would work if I wanted to define this in MATLAB. So I've got MATLAB opened up, and let's see. I'm going to use a capital X for this just to be different. Okay, so capital X equals, we'll put a square bracket on that, and then we start defining our matrix. So we would say 5, comma 35, comma 43, comma 7, and then we insert a semicolon, and that'll tell us, okay, we're on the next row. So 4, 76, 81, 8, and then another semicolon, and then 21, 32, 40, 3, and then square bracket. And I'm not going to put a semicolon at the very end because I actually want to see what the answer looks like when I press enter. So if I press enter, I should get an echo of that response, and it should look something like this. And if you look, that should match what's on the slide, right? 5, 35, 43, 7, 4, 76, and so on and so forth. Sound good? Everybody okay with that? Now, a couple shortcuts that might make your life a little easier if you get to the point where you could start to recognize some of the syntax. If you don't feel like using commas, that's fine. You can use spaces. So I can say capital X equals, and then I can say 5, and then space, 35, 43, 7, and then 4, 76, 81, 8, and then, semicolon, and then 21, 32, 40, 3. You can do that, and then that will work as well. Okay? Everybody okay with this? Notice if you look at your workspace, look what it says. It doesn't give you a value, bless you. It doesn't give you a value like it did before. All it says is 3 by 4, and it says double. Double just means the values are being reported to double precision. But the 3 by 4, 3 rows, 4 columns. So when you're dealing with matrices, you ought to get used to MATLAB reporting them as such. All right? Sound good? Okay. Now another way that you can enter matrices is this, and this is a pretty nifty one. You can go x equals, and then you can say, all right, I'm going to start typing in this first row. So 5, 35, 43, and then 7. And then what you can do is you can actually press enter right now. Okay. Now if you press enter, look what happens. If you look right here on the bottom, it should say continue entering statement. You can go in and then start entering in your next row right here. So you can say 4, 76, 81, 8, then press enter, and then 21, 32, 40, 3. And then when you're done, just close it with a bracket and press enter. If you've got a really, really big matrix that you're trying to define, that's a really quick way of doing it. You know, just use the space bar to separate your values and press enter to separate your rows. That can create a matrix quite quickly. So it's just something to be aware of. That syntax should also work in a script as well. You can press enter and that'll work inside a script. It might be lined up a little differently, but that's really it's really no big deal. All right. So far so good? Okay. A couple other things. So let's see. And I'm just going to, the way this is going to work is, you know, we're going to take the simplest topic with matrices, and we're just going to keep adding to it a little by a little by a little. Okay, so first off, you know, you can define a matrix using numbers or values. That's pretty simple. You can, just like before, you can define a matrix with predefined variables or computations. So for instance, if I want to define a matrix and I want it to be something like A equals, and then instead of typing in a number, if I want to type something in like pi, or the square root of 2, or negative 3.62, or the log of 7. Now, what type of logarithm is this? Pop quiz. That's a natural logarithm, right? MATLAB refers to natural logarithms with LOG, not LN. So Just something to keep in the back of your head. All right, sound good? All right, now one thing that you need to be aware of when you create matrices is that, this matrix had what? 2 terms on the first row? That means every row has to have 2 terms. Like if I went in and said something like 3, it would get very mad at me. Well, it would get mad at me on the upper row. Whoa, what happened there? Yeah, if I put my bracket in, it does not like that. Now, why does it not like that? It doesn't like that because I've got 2 values on this row and I've got 3 values down here. Likewise, if I went A equals, and then let's put it all on the first row, just to keep it simple. So pi square root of 2, and then negative 3.62. And all I did was this. So if I had, let's say, 2 values on the first row, but only 1 on the second, it's not going to like that because the dimensions aren't going to match. I mean, if you've had some experience with computers, you think, well, it's probably going to automatically assign a value of 0 to those entries. No, you actually would have to go in and enter the 0. So this calculation, you can see it's not going to work. Oh, I had a P. Yeah, that isn't going to work as well. You have to go in and say, nope, I'm going to put in that log of 7. All right. So just make sure whenever you're defining matrices that, okay, if you, let's say your first row has 5 terms, well, every row in that matrix has got to have 5 terms. And that might seem something kind of odd to harp on, but I've been doing MATLAB programming for a number of years now, and I can tell you, you start getting into really, really large, complicated programs, and one of the biggest errors or bugs that a user has to go through and fix is making sure that all of the matrices have the right sizes when you start putting stuff together. It's probably the most common error that you have in programming altogether. So it's just something you need to be made aware of. Just make sure that when you're creating matrices or combining matrices that all your dimensions match. It's something I'm going to harp on quite a bit because it's kind of important. All right, sound good? All right, so a couple other matrices that you could create that are pretty useful. Okay, one of them, I'm going to skip this one for right now, but I want to talk about the zeros and ones. 0 matrices and 1 matrices, pretty simple, right? You just, if I say I want a 0 matrix that's 2 by 5, it just creates a matrix that's full of zeros. So, something like zeros, if I said 6 by 7, bam, just a bunch of zeros. Now, that might seem like a complete waste of time, but I can tell you that in programming applications, having a matrix that's full of zeros can actually be quite useful. I know that when I created a lot of my MATLAB scripts for my PhD, what I ended up doing was I was creating these big node and element tables for large-scale finite element analysis. And what I would do is I would create the matrix with a bunch of zeros, and then I would go in and just start filling in the appropriate values. And when you've got a model that's got, tens of thousands or even hundreds of thousands of nodes, it was a way of making sure that the program would spit out the right number of nodes and elements, so it made life actually a little easier. So having a matrix full of zeros or ones, if you had ones, you might say something like 5, 1, it can actually come in handy. Okay, so it's just something to be made aware of. And again, make sure everybody's clear on the referencing. So for instance, this ones matrix says 5, 1. That is a matrix that has 5 rows, 1, 2, 3, 4, 5, but it only has 1 column. Okay, we tend to refer to that as a column vector because it's only a single column of terms. If it was 1, 5, it would be 1, 1, 1, 1, 1 like that, and we would call that a row vector. Okay, so it's just something to keep in mind. Now this one command I kind of skipped. I wanted to wait to the end on this EYE or I. That's on purpose. This creates what's called an identity matrix. Okay. Now you only need one number here because identity matrices are always square. So if I do something like I of, let's say, 4, it automatically creates a 4 by 4 matrix. Okay. Now an identity matrix, you can always characterize that as having ones along what's called the main diagonal, So anywhere where the row and column index is the same, so like this term is on the first row and the first column, this term is on the second row and the second column, third row and third column, etc. All those terms are going to be 1, and everything else is going to be 0. Now, let's be clear, my purpose in this class is to get you all to understand MATLAB, okay? I'm not trying to teach you all linear algebra on top of that. So I'm soft pedaling the matrix math a little bit. But suffice it to say that the identity matrix is one of the most important matrices when you all start to learn about matrix algebra and linear algebra. The identity matrix is called that because it's shorthand for what's called the multiplicative identity. Without getting too far into it, let's just keep it simple. What's 4 times 1? 4, okay. 76 times 1? 76, okay. 1 is, when we're talking about numbers, 1 is the multiplicative identity because anything times 1 is itself, okay. That's what 1 is if we're talking about number theory. It's the multiplicative identity because it doesn't change anything when you multiply things. In matrix algebra, this is the multiplicative identity. If you take a matrix and you multiply it times this, it doesn't change. Okay, so it has a lot of very useful properties in matrix algebra, and I'm just going to sort of leave it at that. We will see an example of this here in a little bit, but I just want to sort of leave it at that. Everybody good? Okay, all right. Now, one thing to keep in mind, you can use these ones commands, these zeros commands, and even some of the stuff that we did for 1D matrices to create some really complex matrices very quickly. So for instance, if I wanted to create a matrix that, let's say the first row did 10, minus 1, 4. So what is that going to do? It's going to start at 10, it's going to end at 4, and it's going to change in increments of minus 1. So it's going to go 10, 9, 8, 7, 6, 5, 4. How many terms is that? 10, 9, 8, 7, 6, 5, 4. That's 7 terms, right? So what I might do is I might say, okay, that's the first row of this matrix. Okay? Then the second row of this matrix might be just ones. So it's got to be 1, 7, right? Because if it's 10, 9, 8, 7, 6, 5, 4, that's 7 terms. I got to have 7 terms on the second row. Make sense? All right. Then I might have something like 2 to 14. Now, is that going to work? 2, 4, 6, 8, 10, 12, 14. That works as well, right? Everybody okay with me on that? Then my next one might be zeros. 1, 7. Then close it up with the bracket, and that's what you should get. Now that was a little bit of a complicated matrix, but that matrix would be, I mean, look at the amount of code that we wrote to define that matrix. That's far less than if we actually went and typed in every single individual value. Went 10, 9, 8, 7, 6, 5, 4. You know, that would, the amount of code it would take a lot more, okay? The big point also that I want to make sure that everybody's clear on is this had 7 terms, this had 7 terms, this had 7 terms, this had 7 terms, okay? If you're going to start piecing them together, you have to have the same number of terms, okay? That makes sense? If I went in and said, you know, nah, let's put 9 terms on this row, it does not like that, okay? So, everybody okay with that? Any questions? All right. Let me go ahead and clear some things before we move on. I want to clear, first off, let me CLC. Let's just do that. Okay? All right, so CLC. Now, when I define that first matrix, I define it with a big X. So I'm not sure if you still have this defined because we've been messing around with stuff. But if you haven't, I'd like everybody to go ahead and define this matrix if you haven't already done so, because I do want everybody to sort of follow along with me on this. So it should be 5, 35, 43, 7, and so on and so forth. So if you haven't already done that, I want everybody to do that. Now, One of the things I like about this matrix is that each of the numbers are unique. Like there's a 21, there's no 21 anywhere else. So that'll help us out when we start referring to terms within this matrix. Okay? So let's keep this simple. Okay? Let's start off with the 32. Let's take the 32 for instance. What row is the 32 in? Third row. Which column? Second column. So if I want to refer to that term, I might say x of 3, 2. Or I'm referring to the X matrix, and I'm referring to the third row, second column. Bam. Okay? So that's something that's going to be pretty important, is that making sure that within a given matrix you can refer to given values. So the 8, what's the 8 going to be? So what would the reference for the 8 be? 2, 4, right? So 2, 4. Make sense? All right. I'm using this really big text here on the screen, so I'm going to clear that and then display that so that way everybody can see that. Okay. Now, here's a really nifty one, okay? Let's say I want to refer to the first row, okay? The first row. All right. Well, I could do that one of two ways. I could say X, I want the first row, and I want all the terms in the first row. Well, how many terms are in the first row? 4. So I could do 1 to 4. I could do that. See how I did that? Bless you. Okay. Another way I could do it is I could say, you know what, let's go back to basics. Let's go back to using those matrices. I want the first row, but I want all those columns. I might say 1, 2, 3, 4. So let's sort of dissect what I've got here. I've got the first row, and then for the columns, I've got 1, 2, 3, 4 in brackets. Okay? Make sense? Now, here's the thing. I'm lazy. Okay? So here's another way of going about it. Okay? Another way of going about it, let me clear this out again, is I can say, all right, I want the first row, but I want all of the columns. And actually, a short way of doing that is to just put a colon. Okay? So just put the first row and just a colon. And MATLAB recognizes that as shorthand for all of the terms in the first row. Okay? So that would give you all of the terms in the first row. If, on the other hand, if I wanted all of the terms, let's say, in the third column, so I want this 43, 81, and 40, I would say X, I want all of the terms in the third column. So technically what this is doing is it's saying all rows, and just the third column. Bam. Does that make sense? Everybody okay with that? That's not bad, is it? That's simple stuff. All right. Another thing you can do is if you really want to get technical, you can get a little fancy with it. So let me clear this out. Okay. So let's say I only want, let's say, this chunk right here, like this part right here, from the 35, 43, 7, the 76, 81, 8. So these 6 terms. Okay. What rows do these terms occupy? 1 and 2. And which columns do these terms occupy? 2 to 4, right? So I can say X, and I only want rows 1 to 2 and columns 2 to 4. Okay, does that make sense? Everybody okay with that? Any questions? I want that to be somewhat clear because what we're going to do here in a little bit, we're going to sort of add to that. Okay. Now, this doesn't show up on your PDF, but it will show up here on the slide. I want everybody to look at this. Okay, one of the most fundamental ways of modifying a matrix is to transpose it. Okay, so now what I want to do is I want to use some of these referencing tools and this transpose command to do some modification. Now here's what a transpose does, okay, and my animation is probably going to cycle through again, so give it a minute. But I've got here a matrix that's 1, 2, 3, 4, 5, 6. What transposing does is it flips terms about the main diagonal. Again, that main diagonal is anywhere where the row index and the column index are the same. You know, this is the first row, first column, second row, second column. So these terms sit where they are, and every other term flips about that diagonal. Now to do that in MATLAB, we do that through using the apostrophe. Okay, so let me show you how this works. So let's define this matrix. So let me clear this out. So A equals, and then what is it? So how do we define that? 1 and 2, 3 and 4, 5 and 6. That looks right, doesn't it? Sound good? Okay. To transpose that matrix, we would say A and then apostrophe. Okay. Now, a couple things that happens when you transpose a matrix. Okay. What are the dimensions of A, of just A? This one up here. 3 by 2, right? Now, what are the dimensions of A transpose? 2 by 3. They flip. Okay. That'll always happen. Okay. So that's something to keep in mind. Okay. Another thing to keep in mind, again, we're flipping about that main diagonal. Those terms do not change. For instance, what's in the first row, first column? What's in the first row, first column? What's in the second row, second column? Second row, second column is 4. Okay, so that doesn't change as well. Sound good? Okay. Well, if that makes sense, then let's play around with this for a little bit. So this is something we've soft pedaled for a little bit, but I really want this to make sense. So if I create a vector, it looks like this: -6, 2, 6. Now remember, you can put brackets in if you would like. It doesn't really matter. Oh, that's supposed to be an equal sign. You can put brackets in if you would like. It really doesn't matter. But if I press enter, what do I get? I get -6, -4, -2, 0, 2, 4, 6. I get 7 terms, right? But that's a row of 7 terms, right? That's a row of 7 terms. That matrix is, what are the dimensions of that matrix? 1 by 7, right? Make sense? Why don't I do this instead? Why don't I do that? Now I get a matrix that is 7 by 1. Now the brackets or parentheses, they're not necessary. I tend to like to use them just to make sure I'm identifying what's a matrix and what's a given value. It's just something to keep in mind, okay? Using that apostrophe and knowing when to use it, that'll make all the difference later on when you're modifying matrices. And I think you'll see that pop up here in a quick second. Everybody with me so far? Everybody good? Okay. Now, if you understand that, then we are going to create a matrix and we're going to modify it a little bit. So what I want to do is I want to make sure that everybody's clear on how to do all this this matrix modification and how to do all of this referencing. So I want everybody to create a matrix full of just a bunch of random values. Now, I'm not saying you make them up. Get MATLAB to make them up for you. MATLAB has a random number generator inside it. Okay, so if you use the rand command, we'll say rand from 4 rows and 5 columns, it'll generate a bunch of random numbers. And these have a lot of very strong applications in programming and whatnot. For instance, I know you all probably played video games before, and you're playing a video game and some enemy pops up that you didn't expect. Well, how do you think the game made that happen? Well, it was a random number generator. It just, based on that value, here's the enemy that pops up. So that's just one simple example, but they have a number of other examples in computations. So let me clear this out. So CLC, then we'll say y equals rand 4, 5. Okay, now mine looks a little different because I'm using this big text. Let me see if I can, hold on, let me see if I can change, I'm going to change the text, maybe squinch it down a little bit. Let's do 16. Let's see why. There we go. So now, obviously, term by term, your matrix is not going to look like this, or the one on the slide, or the one on your friend's computer next to you. These are random numbers, so they're all random. Okay. So, however, I do want to do some modifications to some of these terms. So let's see if we can do some modifications. Now let's just go back to basics. Okay. If I do x equals 2, how does MATLAB interpret that? Well, it starts off interpreting everything on the right. So it has 2, right? And then it assigns that term to x. Okay? So why don't I do this? Let's take this term right here, that term right there, and I want to make that term 4. So how do I do that? Well, what term is this in the matrix? What are its coordinates, if you will? 2, 2, right? So what I'm going to do is this. I'm going to say y, and I'm going to say the term in the second row and the second column. I'm going to set that term equal to 4. Now when you press enter, what should happen is nothing else changed except what we said. Okay? Make sense? Everything else stayed the same except for that second row and second column. That term is now a 4. Okay? Let's move on. Let's say I want to take this term right here. On mine it's 0.9595. Let's take that term and set it equal to pi. Okay, so what are the coordinates of that term? 4, 1. So y of 4, 1 is pi. So you'll notice the 4 stayed, but this is now a pi. Sound good? Okay. Now we're going to get a little fancier. Okay. Now what I want to do is this. Okay. I want to take this term, and this term, these 3 terms right here, and I want to turn them into 5, 8, and 11. Okay. So let's start off with the reference. Okay. This term, and this term. What row? 3. What columns? Not 1 and 3. 1, 2, 3, right? So how about this? How about the third row and the first to third columns? See that? Now, what did we say? 5, 8, and 11? Now, I could do 5, 8, and 11, or I could do 5 in increments of 3 to 11. Does that make sense? I really want that to make sense. Everybody okay with that? So if I press enter, walk back over here. That's what we got. Did everybody get that? Everybody get that on their screens? Okay. Now, here's the interesting part. Okay. Let's say this column right here. This column, I want to take this column and I want to make it 2, 4, 6, 8. Something like that. 2, 4, 6, 8. So, which column is this? 4. Which row is it? All of them. So how about this? Y, and then all the rows in the 4th column. Okay. Now, what do we say? 2, 4, 6, 8? So how about this? 2, 2, 8. All right. Now let's say you do that. What happens? Well, that works. But let's say that I did something. Let's say I did this. Let's say you didn't want to use that must have been updated from the last edition of MATLAB. I remember when I wrote that on my PhD, that gave me all sorts of problems. That when I wanted to start concatenating matrices, I had to put my little apostrophe there. Never mind. That was supposed to be a big point. I remember when I did my PhD and I had to do, if I wanted to start changing values, I had to include that apostrophe there. MATLAB got so mad at me. My code has so many different apostrophes. I lost my mind trying to track all those down. So you all don't have to deal with those pains. Long and short of it is we can go through and replace values within a given column as well. I personally would rather include the apostrophe. That's just me. And I'll say this, if you're trying to replace multiple rows and columns, then you need, I know for a fact you need to make sure the dimensions match. Everybody okay with this? Okay. Now, a couple other things. All right. Here are a couple MATLAB commands that make your life a little easier. Okay, now I want everybody to make sure they understand the difference between the length command and the size command. The length command is primarily used for vectors. The size command is primarily used for matrices. So let me ask you this. What is the size of this matrix right here? 4 by 5. So if I do size of y, I get a row vector that's 4 by 5. Okay? Does that make sense? Is everybody okay with that? All right. Now, I created a vector a little bit higher up, this b, I think it was a b vector. Yeah, I created this b vector. Now, that has 7 terms. If I do length of b, I get 7. Okay? Does that make sense? Okay. So I just want everybody to understand the difference between the length command and the size command. Length is for vectors. Size is for matrices. Sound good? Now, let me show you something. So let me go back to, let me clear all this out. So here's my Y matrix with all the stuff that I've changed. A lot of the commands that we defined before will work, but they tend to work on a column by column basis. So, like for instance, mean. Okay, if I calculate the mean, what it's doing is it's calculating the average, but it's calculating the average on a column by column basis. So this 5, that's the average of this column. This value is the average of that column. This is the average of that column. You could take the average again and get the average of the whole thing. Same thing if you did something like sum. That'll give you the sum of each column. If you want to add up everything, a trick is to just take the sum of the sum. And then that'll add up every term in the matrix, because it'll start off by adding all the columns, and then it'll add all the rows. It's just something to keep in mind. All right? But a lot of those, the sum commands and the statistics commands, they will work, but they tend to work on a column by column basis. I'll say this, that actually will make your lives easier more often than not when you're dealing with saving and loading data files. Like for instance, you all remember that gross vehicle weight problem that we did, where you all had all the thousands and thousands of vehicle weights on that given road or that given interstate? Well, if you notice, that data came in columns, right? Like there was a column of data, a column of data, and a column of data. If you just hit mean, type in mean, and calculate the average of each of those columns. So when you're doing data analysis, the fact that MATLAB operates like this, that it takes the average of each column, or the sum of each column, or so on and so forth, that'll actually make your life a little easier when you're doing those type of operations. So just something to keep in mind. That's a great question. All right. How about this? All right. So here's why, right? Okay. You're asking, can you take the sum of each row? Why don't you do this? What did that do? Think about what that did. What that did is it transposed the matrix. So now you're not taking the sum of each column, you're taking the sum of the transpose. So that's going to be the sum of each row. Look how many terms you've got. 4, not 5. That's a really good question. And if you're wanting it to display up and down, then do the sum of y transpose and then transpose that. That's a good question. Does everybody understand that? Does everybody understand what we just did? We flipped the matrix, summed each of those columns, which is effectively summing the rows, and then if you want it up and down, transpose it again. That's a great question. Anybody else? This is good stuff. This is the stuff that you want to be clear on. Sound good? All right. Now I'm going to bring it back a little bit. It's been a while since we've done this, but this was January. This was a while back. If you recall, when we were using the Casio, to do some calculations. One of the equation solvers that we used in the Casio was to solve simultaneous equations, right? Remember, we had 2x2 equations and we had 3x3 equations. Y'all remember that? The Casio is limited to that. It can only do, like, past 3x3. It really, I mean, there are matrix commands, but it gets a little tough when you get past dimensions of that size. The nice thing about MATLAB is it can solve matrix, much larger than 3x3. I mean, we're going to do a 10,000 by 10,000 here in a second. And now that might seem a little crazy, but in practical settings, if you're doing something like a finite element model, which you all might learn about later in your engineering career, that's actually not that unheard of. Okay, that's one of the things that makes computers so useful. A computer is really good at calculation over and over and over and over and over again. That's what makes computers so powerful. That's how they're able to run the software that we run on them nowadays. But I do want to, without going off on a tangent, I do want to discuss how MATLAB can be used to solve an expression like this. So let's go through the theory first. So you all have seen problems like this before, right? I mean, we've done them in here. 3 equations, 3 unknowns, or 2 equations and 2 unknowns. Everybody in here has seen a problem like this, right? Now, what we can do is we can write this problem in matrix notation. So everything over here on the right side of the equal sign becomes a column vector, right? And everything over here becomes a square matrix, right? Okay. So what I want you all to do is go ahead and define these matrices, this one right here and this one right here. Now I'm going to go into my MATLAB interface. I'm going to clear out all these variables because I got a lot of stuff that I've created over here. So clear and CLC. So remember, clear will clear out all the variables in your workspace. CLC will clear your command window. Well, let's start off with the A matrix. So 5 minus 3, 2, 3 minus 3, 7 minus 4, minus 2, or no, yeah, minus 4, 7. Let's see, did I get everything right there? 2. Oh, nope. That is a minus 2 right there. Okay. All right, so your A matrix should look something like that. Now, if you notice here in the slide, look how I created the column vector. I said B equals, and I said 1.2, 0.6, and then 0. But because I want a column vector, I need to transpose it. Transpose it. I transpose that with the apostrophe. Okay. Sound good? So everybody got those created? Okay. Now, one of the things that you know, in my opinion, it's a strength of MATLAB, but I think when you're first starting to learn MATLAB, you might think it's a weakness. Is that MATLAB has multiple ways of doing the same thing, okay? And I know a lot of times when you're first learning MATLAB, you're like, here's the problem, just tell me how to get the answer. And many times there is a simple answer. Many times there's not. For instance, if you want to solve a simultaneous set of equations, there's actually a couple different ways of going about that. Now, ultimately, what we need to do is we need to take the inverse of this matrix and multiply it times that vector. And when you're using a Casio, that's essentially what it's doing. That's essentially what Casio is doing. There's a couple ways of going about that. One of them is to use the inverse command. So I can say, I can go into MATLAB and I can say x equals the inverse of A times B, and I'll get an answer. That's one way of doing it. Now, in matrix algebra, the inverse is no different than taking a matrix and raising it to the -1 power, right? Think what happens if you take 3 and you raise it to the -1 power? You get 1 over 3, right? So that's one way of doing it. So I can say x equals A raised to the -1 times B, and I get the same answer. Okay. Now, another one, a new one, this one's really unique to MATLAB, is to use an operation called left division. And it's really just for this application where you take A and you divide it by B, but you divide it using a left division key. It's right above the equal sign. You'll get the same answer. Okay, that's one that's unique to MATLAB. Okay, now I like the fact that MATLAB is versatile, that it will do a number of different it will interpret a number of different ways of solving different problems. As long as you've written the program correctly and you've defined your logic, you can get the same answer. But I think the headache or the question is, what's the best method? In other words, I just did 3 different solution strategies and got the same answer. Now, if you were writing a program, which one should you use? I don't know. How would you determine that at all? I mean, what's a good way of determining what's the best way? Well, if they're all yielding the same answer, I would propose that the best answer is the one that gives you the fastest answer, right? You know, let's sort of see how that would work. Now, I'm going to be honest. If you tried to time the speed of MATLAB answering the problem we just proposed, you're not going to get meaningful results because your computer is spitting these results out like that. I mean, a 3x3 system is nothing to a computer that can run Windows 10. Okay, it's nothing. A 10,000 by 10,000 system, that's something a little different. Okay, so let me open this script, and I'm actually going to run it right now so that it'll have time to run. And let me show you what it's doing while it's running it. So I have a script on Blackboard called speed test. If you all haven't run that, go ahead and run it. Let me hit run and let me show you what it's doing. So let's take it one line at a time. So the first thing it's doing is it's clearing out the command window so it doesn't show anything on the command window. And then the first thing it's doing is it's defining a matrix and a B vector. And if you notice, they've got 10,000 terms in each row and column and etc. So this is a really big system. And again, this isn't that unheard of if you're doing some finite element stuff, mechanical folks who might be doing some finite element analysis, designing some engine or some gearbox or something for your senior design project. This isn't that unheard of. I mean, I'm just telling you. Many of the models I ran for my PhD were much larger than that. But this is just really to sort of emphasize what's going on. Now, that's a lot of zeros. Did you have one of the semicolons off? Oh, you just, oh, okay. Yeah, that's a big matrix, isn't it? Yeah. So yeah, you can kind of get the scale as to what's going on. You know what I mean? If we printed off a 10,000 by 10,000 matrix on 8.5 by 11s, we could probably tile the room with it, you know, and then some. Now, what this code is doing is it's doing 3 calculations, one using the inverse command, one using the -1 exponent, and one using this left division. But before and after each one of these codes, we've got a tick-tock. Everybody see that? And tick-tock, did you leave a semicolon off?
Yeah, I forgot that.
Well, it's on, that code is on Blackboard, isn't it? Yeah, I was going to say, the code's on Blackboard. Did you open the one on Blackboard? Oh, well, yeah, that'll do it. If you need to close MATLAB, I would. All right. Now, let me sort of back up and explain what's going on with each of these codes. So let's take X1. We've got this tick and tock. Essentially, what the computer's doing is, imagine the computer has a stopwatch, and the computer says go, and then it runs the code. And whenever the tock, it says stop. Okay? So what the computer is doing is it's measuring the amount of time it takes to run each of these lines of code. So one for X1, one for X2, and one for X3. Now, if you look at your display window, you should get something like this. Okay, so if you look at, here's my screen. Now, your numbers may be a little different, but you should be getting the same scale. You should be getting that line 1 and line 2 took some amount of time, but line 3 took a lot less. Did everybody get that? Did anybody not get that? I'm just curious. Anybody not get that? I ran this on my my Microsoft Surface, my Surface Pro, and it came up to something like 30 seconds for these two, and I think it was like 12 for the other, something like that. What was it? Yeah, okay. Yeah, so I got 35 seconds and 12 seconds. So the idea is that this command was written, this left division, that command is defined within MATLAB to be the most efficient at solving these types of equations. So if you're writing a script, that's what you would want to use. Now, there are some disadvantages to using this left division. You don't actually get the inverse. Like if you actually need the inverse of a given matrix, you don't get it out of this. So it's just something to keep in mind. Okay? So everybody okay with this? The big point is that when you're writing a program, you know, when I was doing my PhD, there was a couple of different ways I could have tackled some problems. Well, I'd write, you know, some code, I'd time it, whichever one was the fastest, that's the one I would use. I mean, some of these scripts that I was running, I mean, I would run it on Friday and come back on Monday and it was still running, you know, so yeah. And I was using a pretty high-end workstation. It's because some of the computations for those stuff it just takes a while. It is what it is. So doing this type of analysis, it matters. Okay, it really matters. All right. Any questions on this? Okay. Couple other things. Let me go back to that that X matrix that I created back at the very beginning. I think I cleared it out. Whoops. Let's recreate that matrix again. Okay. X equals, where we have 5, 35, 43, 7. And we had 4, 76, 81, 8. Then we had 21, 32, 43. Okay. All right. So this is that matrix we were dealing with back at the beginning. Let's say I do this. X squared. Whoop. x squared. It does not like that, okay? Why does it not like that? Well, it doesn't like it for the same reason that it didn't like it before. Remember the whole dot operator? We need to use a dot operator, okay? Now, when I said x squared, what I really wanted it to do was square individually each of those terms. So that's what that dot operator does. Element by element, I want to square each of those terms. So, 5 squared is 25. 4 squared is 16. 3 squared is 9. 7 squared is 49, etc. I want to square each of those terms. Okay? Make sense? So this is where that dot operator is really gonna matter. Okay, using that appropriately. One point I will mention, and this is a word of caution, I want to create the following matrix. So C equals, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh. All right, so C equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me clear all this out. Now, let's say I want to square individually each one of those terms. How would I do that? C, then dot, caret raised to the second power, right? So C dot squared, and then that's what it did, right? 1 squared is 2, 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, so on and so forth. Sound good? Now, if I leave that dot off, however, it does not yield an error. It in fact yields an answer, and a much different answer. Okay? Now, why is that? Okay? Takes a little bit of explanation, and I'll do my best to keep it short, but I want everybody to understand this. So, if you recall, I mean, what does MATLAB stand for? It stands for Matrix Laboratory, right? MATLAB was written to do matrix math, okay? So that's its default, is to do matrix multiplication, okay? That's what it's doing right here, is it's doing matrix multiplication. The only reason it gave us an answer is because the dimensions worked out. Now, I've been saying this whole dimensions workout thing for a while. Let's sort of bring it back a little bit to matrix multiplication. I'm sure you all have done this stuff before, whether you did it in high school or you've done it sometime here at Marshall. But if you recall, if you've got, let's say, 2 matrices that you want to multiply, I mean, how does this work? Well, if I've got a given term I want to multiply, I take all the terms, let's say, in this row, all the terms in, say, this column, and I multiply and add them up, right? So what is this, like 1 times 9, 2 times 8, 3 times 7, right? And 4 times 9, 5 times 8, 6 times 7. Y'all remember doing that? Y'all remember that? One way that you could do this graphically is you could take your first matrix, put it over here on the left, your second matrix, put it over here on the top, and then if you've got, let's say, a given term, just go this times this plus this times this, and then just go down like that. And this multiplication right here, it wasn't taking each term and squaring it. It was literally taking matrix A and multiplying, or matrix C, multiplying it times matrix C again. So it was going, this times this plus this times this plus this times this. And that's why the answer looks a lot different than it does here. So I guess my only point, or my word of caution, would be just make sure that you're aware that omitting the dot operator doesn't necessarily mean that the answer is going to be wrong. It just means it may not be what you intended. Just make sure you're aware of that. Okay? If you intend to perform matrix multiplication, the dimensions have got to match. So the number of columns in the first matrix has to equal the number of rows in the second. And that's something you all probably learned when you took pre-algebra or whatever you took in high school or something like that. Make sense? Again, I know this was a lot of referencing stuff and a lot of, maybe a little dry for today, but this stuff needs to be somewhat clear for what we do next, this whole saving and loading data and for loops and things like that. I really want this to make sense. Sound good? I have no homework for you today. You have a homework due to me, though. So that's all I've got. I will see you all next week. You all have a great weekend. You have a question? Hold on. Let me